Thank you for keeping up with us. This time around, we're going to look at partial differentiation, and we are going to have 5 objectives for this topic. The first objective is to define partial derivatives of a function of 2 variables. The second one is to differentiate partially from first principles. The third one is to differentiate a function of 2 or more variables. The fourth one is to solve problems involving small changes or errors using partial derivatives. The fifth and the last one is to find stationary points of functions of 2 variables. We will go quickly to the first objective and define what partial differentiation is. For example, we have a cylinder. We know that the volume V of a cylinder is given by V is equal to pi r squared h, where h is the height of the cylinder and r is the radius of that cylinder. Someone may be interested to know how V changes with r if h is kept constant, or how V will change with h if r is kept a constant. So in this case, because we have a variable V dependent on 2 other variables, then this quantity will be affected if you change r, or if you change h, or if you change both r and h. And that is why we are going to look at partial differentiation. And partial differentiation basically deals with quantities with more than one variable. So here we define partial differentiation by partial derivative of V with respect to r is equal to differentiate V with respect to r, keeping h a constant. That is the definition of partial derivative of V with respect to r. If we keep r constant, we can also vary V by varying h. So we have partial derivative of V with respect to h is equal to differentiate V with respect to h, keeping r constant. That is the partial derivative of V with respect to h, keeping r constant. Both these two definitions are what we call partial differentiation. So it basically deals with cases where a quantity is determined by more than one variable. So you can keep h constant, vary r. You can keep r constant, vary h. And in both cases, V will also change. At the same time, you can also vary V by varying r and V simultaneously. So if we look at it a step further, we have partial derivative of V with respect to h. If we keep r constant, you're going to take everything that is not h outside. So we have pi r squared is kept constant. Then we differentiate with respect to h. The only variable in this case is h, so that we have pi r squared times h times 1 raised to 1 minus 1. Because if you have y is equal to ax power n, then dy over dx is equal to n times a x power n minus 1. In our case, n is 1, so we subtract 1 from 1, then we pre-multiply by that power. Here we're going to get pi r squared times h raised to 0. Remember, any number a raised to 0 will always be 1. So this gives us partial derivative of v with respect to h is equal to pi r squared. You can also get the same if we keep h constant and vary r. So what will happen? We are getting partial derivative of v with respect to r, keeping h constant, is equal to, take everything that is not h outside. everything that is not r. So we have pi times h. We differentiate with respect to r. Our variable is r squared. So this gives us pi times h times 2 times r raised to 2 minus 1, giving us 2 pi r times h. That's the partial derivative of v with respect to r. So both these two are what we call partial derivatives of v. First with respect to h, keeping r constant, and second with respect to r, keeping h constant. That's what we call partial differentiation. And in partial differentiation, the rules of differentiation still hold. That is product rule, quotient rule, we have the chain rule. All those rules of differentiation will apply. Let me give you one example. Here. We have a function z, which is dependent on both x and y, is given as follows. So we have z is equal to 4x plus 3y, multiply that by 2x minus 2y. We're supposed to differentiate that partially, first with respect to x, then with respect to y. So we can apply, because this is a product, we can apply product rule but with partial derivatives. We call the first bracket u, we call the second bracket v. Second bracket is v. So here we note that u is equal to 4x plus 3y and v is equal to 2x minus 2y. We are going to do it using product rule, and we repeat the same equation using an expansion of that. So because u depends on both x and y, we can get two partial derivatives. So we have partial derivative of u first with respect to x will be equal to, we are keeping y constant, so we have partial derivative with respect to x of 4x. We add partial derivative with respect to x of 3y. Remember, we have a constant here, y, because we are treating it as a constant. We are assuming that u varies with x only. So here we are going to have 4 is a constant, we can put it outside. Then we have partial derivative with respect to x of x. We put a bracket plus, if you differentiate 3y with respect to x, because it's a constant, you get 0. And this gives us 4 times partial derivative with respect to x of x plus 0. And this gives us 4. So partial derivative of u with respect to x gives us 4. We can also have partial derivative of u with respect to y, keeping x constant. So we are going to have partial derivative with respect to x of the first term here is 4x. Then we add partial derivative with respect to, sorry, this is supposed to be y here, partial derivative with respect to y of second term here is 3y. Remember here x is treated as a constant, so partial derivative of u with respect to y is equal to, because there is no y here, 4x is a constant, and if you differentiate a constant you get 0. Then we add 3 is a constant, it can sit outside here. Then we have partial derivative with respect to y of y. This gives us 0 plus 3 partial derivative of y with respect to y gives us 1. 1 times 3 is 3. So this is equal to 3. That is partial derivative of u with respect to y. We can put this one in red so that we can easily identify them as so. So we have partial derivative with respect to y is equal to 3. Partial derivative with respect to x is 4. We can also do the same for v. Then we have partial derivative of v with respect to x. So we have partial derivative of v with respect to x is equal to partial derivative with respect to x of v is 2x. Then we have minus partial derivative with respect to y of 2y. Remember, here we are keeping y to be a constant. This gives us 2 can sit outside there, and we have partial derivative with respect to x of x. Then we have minus 2 is a constant. Partial derivative of x with respect to y is equal to 0. Because 2 is a constant, we can take it outside. Then we have 2 times partial derivative with respect to x of x. We subtract. If we are treating y as a constant here, then the whole of this expression will be 2 times 0, which gives us 2 minus 0, which is actually equal to 2, and that is the partial derivative of v with respect to x. We can also get partial derivative of v with respect to y, so that we have partial derivative of v with respect to y is equal to, we are treating x in this case to be a constant. So we have partial derivative with respect to y of the first term in v is 2x. We subtract partial derivative with respect to y of the second term is 2y. We are treating x as a constant. So the first term here, because it does not have y, becomes 0, then minus. These 2 can come outside the bracket, the derivative, and we have partial derivative of y with respect to y. This gives us 0 minus 2, which is equal to minus 2. That is the partial derivative of v with respect to y. Now we can identify those ones for easy reference. So we have, this is partial derivative of v with respect to x, and this is the partial derivative of v with respect to y. Partial derivative with respect to x, partial derivative with respect to y. Now we can combine these results. So we have 4 results, 1, 2, 3, and 4. Because z depends on both x and y, then we can have partial derivative of z with respect to x. Then we can also have partial derivative of z with respect to y. So let us write this one here because of space. We can write this one because of space. So let us find partial derivative of z with respect to x. Partial derivative with respect to x. Using product rule, we have u times partial derivative of v with respect to x plus v partial derivative of u with respect to x. Our objective now is to substitute them into that. Our u is the first term here is 4x plus 3y. Then partial derivative of v with respect to x. Partial derivative of v with respect to x, where is it? It is this one here, which is positive 2. So we multiply here by positive 2. We add v is the second term in z, which is 2x minus 2y. We are multiplying that by du with respect to x. That's partial derivative of u with respect to x. Partial derivative of u with respect to x is 4, so we multiply this by 4. Then we open the brackets with 2 here. 2 times 4x is 8x plus 2 times 3y here is 6y. Then we add 4 times 2x is 8x minus 4 times minus 2y is minus 8y. Then we put like terms together. 8x plus 8x is 16x. 6y minus 8y is minus 2y. That is, partial derivative of z with respect to x is equal to 16x minus 2y. We can also get partial derivative of z with respect to y, which will be equal to, using product rule again, it is u multiplied by partial derivative of v with respect to y. We add v times partial derivative of u with respect to y. We substitute, then we get our u is the first term, which is 4x plus 3y. Then partial derivative of v with respect to y is negative 2. So we multiply here by negative 2. We add v is the second term, which is 2x minus 2y. Multiply that by partial derivative of u with respect to y. Partial derivative of u with respect to y, where is it? Partial derivative of u with respect to y is 3. So we have to multiply this by 3. Now open the bracket. Minus 2 times 4x is minus 8x. Then minus 2 times 3y is minus 6y. 3 times 2x is positive 6x. 3 times minus 2y is minus 6y. We put like terms together. We have minus 8x plus 6x is minus 2x. Minus 6y minus 6y is equal to minus 12y. That gives us partial derivative of z with respect to y is equal to minus 2x minus 12y. That's what we obtain. Now you can put them in red for easy identification. That is the first part, and that is the second part. So if a function has more than one variable, then you can hold one constant and treat the other as a variable. Then we can interchange those two and see what we get. That's what you call partial differentiation. Perhaps we do another example, and we can repeat that same question by expansion. So you can expand this one first, this bracket, then differentiate partially with respect to x and partially with respect to y, and see if we are going to get the same result. So let us do exactly that. First of all, we expand this. We expand that. So we multiply 4x by this bracket, then we multiply 3y by that bracket, remove the brackets, put like terms together, and then we start doing partial derivative. These are the two that we have obtained using product rule. To see if you can get the same result if we expanded it, and I'm sure we will. So you can use either of those methods. Allow me to wrap right from here. Then we use that area to expand it. So allow me to wrap up to there. We wrap up to this end here, like so. Now let us expand this. Z will be equal to, we open 4x into 2x minus 2y. Then we have plus 3y into 2x minus 2y. Opening the bracket gives us 8x squared. Opening the bracket gives us minus 8xy. Open the bracket gives us positive 6xy. Open the bracket gives us minus 6y squared. That is z after the expansion. Now let us partially differentiate z first with respect to x. So we have partial derivative of z with respect to x will be equal to partial derivative with respect to x of 8x squared minus partial derivative with respect to x of 8xy plus partial derivative with respect to x of 6xy minus partial derivative with respect to x of 6y squared. When we are doing partial with respect to x, we treat anything that is not x as a constant. So here we'll take 8 outside, then we differentiate with respect to x, our x squared minus 8 is a constant, partial derivative with respect to x. Because y is a constant, we can still take it outside. Then we are doing partial derivative with respect to x plus 6 is a constant, y is also a constant there, partial derivative with respect to x of x minus. Here we are treating both 6 and y squared as constants because we are holding x as the only variable, so this will give us 0. Simplifying this one gives us, if you differentiate x squared with respect to x, we have 8 times, bring the 2 down, multiplied by x raised to 2, reduce it by 1. That is how we differentiate. Then we have minus 8y, we have x raised to 1 minus 1, then we have plus 6y, we have x raised to 1 minus 1. I didn't bother to put those ones together first, but we get the same result. So this gives us 16x. When we work this one out, x raised to 0 will give us 1, so this is minus 8y, plus this gives us 6y x power 0, which gives us positive 6y, and that is minus 0. Now put like terms together, this gives us 16x minus 2y. If you look at that, what we get is dz partially with respect to x, and that is exactly what we got here. So using expansion or using product rule, we get the same result. So we can identify this one as the first solution with respect to y. We can also now partially differentiate z with respect to y, holding x constant. So we have partial derivative of z with respect to y is equal to partial derivative with respect to y of the first term is 8x squared. We subtract partial derivative with respect to y of the second term is 8xy. Then we have plus partial derivative with respect to y, partial derivative with respect to y of 6xy. Then we have minus partial derivative with respect to y of 6y squared. Because we are doing partial derivative with respect to y, we hold x constant, and this becomes, we can take 8 outside, partial derivative with respect to y of x squared minus 8 is constant, x is also constant, partial derivative with respect to y of y. Then we add 6 is a constant, x is a constant, partial derivative with respect to y of y minus 6 is a constant, partial derivative of y squared with respect to y. Now x is constant because we are treating y as the only variable. So the first term here gives us 8 times 0, because if you differentiate partially x squared with respect to y, because x is a constant, gives us 0. Now this is minus 8x, we are differentiating y raised to 1, we subtract 1, we multiply by 1 there, then we get plus 6 times x times y raised to 1 minus 1, because we have multiplied by 1 there, and this gives us minus 6 times 2 y raised to 2 minus 1. Simplifying it gives us the first term is 0, this term is minus 8x, y raised to 0 is 1, plus 6x, y raised to 0 is 1, so we subtract 12 times y. This gives us minus 8x plus 6x is minus 2x minus 12y, that is partial derivative of z with respect to y. Then we can look at what we obtained. That's exactly the same thing that we obtained. So expansion gives us the same result. We can put this one in red for ease of identification. So you can use either first you expand it, or you use the product rule if you have a case like this one. So you have observed we can get the same result, but of importance is if you have a function of more than one variable, you can hold one constant, treat the other as a variable. Then you can hold r constant, treat h as a variable. Then you can get partial derivative of v with respect to r holding h constant, or you get partial derivative of v with respect to h holding r constant. That's what we call partial differentiation, and the rules of differentiation still apply in both cases. In the coming lesson, we will look at application of this partial differentiation in small changes. We also look at how to apply partial differentiation to get the turning points when you have a variable that has more than one dependent variable. So up to there we want to stop, and we'll meet in the other lesson where we're going to look at the other part I've just mentioned. So if you have a problem, you can let us know so that we see how we can move forward together. Up to that point, I want to thank you very much for getting time to watch this one. Thank you very much, and we'll meet again in the next lesson.